Hi guys, welcome to Tech Talker. In this video, we are going to discuss about what are containers. So let's get started. The agenda for this video is we will discuss what are containers, then we'll look at some stats about containers, we'll look at the benefits of containers, we'll see how containers differ from virtual machines, we'll answer a question that do containers have an operating system, and then we'll see what's the difference between a containerized process and a normal process. We'll see the backbone of containers, like what powers containers to run the way they run today. So there are two operating system concepts that help in powering containers, that are Linux namespaces and Cgroups. So we'll have a look at them. So let's get started. So the first thing is, what are containers? A container is a standard unit of software that packages up code and all its dependencies so that application runs quickly and reliably from one computing environment to another. This is in contrast to deploying only your code artifact on a virtual machine where all the dependencies are installed as and when required, and to deploy new code, you get a new code artifact on the VM and run it. Additionally, you install any new dependencies if required. So the main point over here is it packages up the code and all its dependencies together. Previously, what we used to do is we have a virtual machine and then we have all the dependencies installed on that virtual machine, and then we just take our code artifact and deploy it on that machine. Let's say that tomorrow there is some new dependency required, then what we will do is we will install that dependency on the machine and then deploy the new code artifact and run it. But in case of a container, the code as well as any dependencies it required, its dependence on the underlying system is very limited. Because the dependency on the underlying system is very limited, it can be taken from one computing environment to another reliably. So the second point is, we can build a container locally, take it to any machine and run it. It contains the needed dependencies. Its dependency on the underlying system is very limited. We'll talk about what dependency it has on the underlying system. Containers provide increased portability, run them anywhere. So since they already contain their needed dependencies, they are very portable, we can run them anywhere. The next point is consistent operation between environments. The container can be executed with the guarantee that the execution environment exposed to the application is the same in development, testing, and production. We can be assured, like before, we might have issues like the dev environment differs from the staging and production. Using containers, we can guarantee that the application will behave in the same way wherever you take it. That's for the simple reason that it contains its dependencies. So the next point is that, what do containers do not contain? So containers do not contain operating system kernels, which makes them very lightweight. In an operating system, right, the kernels part is quite heavy. When containers do not contain kernels, it makes them very lightweight. They use the kernel of the underlying host system. Because of this, they consume less resources and they boot in seconds versus minutes for virtual machines. So we'll go into detail how virtual machines differ from containers, but this is one of the primary differences between a virtual machine and a container, which makes containers very lightweight compared to virtual machines. And because they do not contain a kernel, they can boot in seconds versus minutes. So the next point is, container have features to allocate resources to containers and run them securely, protecting other containers running on the same host and the host itself from a malicious container. In the agenda, I told you about two Linux name features, which is Linux namespaces and Cgroups. And because of this, we can allocate resources to containers. Like a particular container cannot consume more than certain CPU or more than certain memory, and also they do not consume all the resources, not allowing other containers to run. Also, one container will not be able to compromise code running in another container because of these features. And then we move on to the next point. At the core, they are running a single process in an isolated environment on the host machine. So they are given their own isolated environment in terms of process, memory, network on the host machine. I hope from this slide it's clear to you what containers are. Let's move on. to some stats about containers. So containers are rapidly growing because of the flexibility they provide. According to a Gartner report in 2019, by 2023, 70% of organizations will run two containerized apps in production. So that's at least two containerized apps in production compared to 20% in 2019. And another report is by CNCF, which is the report in 2020, that 92% of the respondents use container in production, which is a 300% increase from March 2016. It was 84% in 2019 and 73% in 2018. So as you can see, usage of containers is increasing. And according to the same survey, 23% of organizations run more than 5,000 containers in production, which is up 11% from 2016. So there is a lot of room for growth for organizations to move towards containers. Let's move on to the benefits of containers. So when we couple containers with Kubernetes, right? Kubernetes is an orchestration platform for containers that helps us run and manage containers. So when we couple it with Kubernetes, it makes a very powerful way to run applications in production. Kubernetes has a lot of features to run containers in production. If I give you an example of a feature, when a container dies, auto restart the container. So that's, and then scheduling of that container on a node. So these are some of the features that Kubernetes provides, and this makes a very powerful combination to run apps in production. And the next point is, since they boot in seconds versus minutes for virtual machines, we get benefit of rapid auto scaling. Our let's say we have sudden spike in traffic, then containers can increase rapidly to accommodate the increase in requests. And then the next benefit is consistency between environments, which we already talked about. This is because they already contain the needed dependencies and have very limited dependency on the underlying host. The next point is optimum resource usage. So this point deals with, like, let's say you run your applications on separate virtual machines, right? So the kernel consumes lot of resources. Every time you want to run a small application that consumes, like, let's say very less CPU and very less memory, you need to back it with a kernel that consumes lot of resources and lot of memory. When we run multiple containers on the same host, like, we can leverage the same kernel to run multiple containers, and also we get the benefit of virtual machines, right, the isolation. So in that way, containers help in optimum resource usage. The next point is rollbacks are easier. So we can replace the container in seconds versus roll back the code. So in virtual machines, let's say we want to roll back the code, right? So we will redeploy our old code artifact on the machine, and our code will be rolled back. But for containers, it's just easier, just remove the old container and put the new container. It also takes care of any underlying dependencies that we might have removed or installed. So rollbacks are easier in that way. And the next point is, it makes local development easier. So you can run third-party software on your local using a container versus installing all the tools on your machine. Let's say you are doing development and you want to install tools like Kafka, Elasticsearch, PostgreSQL, MySQL on your local machine, right? Installing them on your local machine is very time consuming. You need to figure out all the dependencies that they may require, follow their installation procedure. Like on their website, they have multiple steps to install that, versus just take a Docker container and run it on your local machine. So it will start working, which makes local development easier and faster. So let's move on to containers and virtual machines. So let's compare how containers differ from virtual machines and how much they are same. What are containers? So containers are also basically a form of operating system virtualization. Like virtual machines, virtual machines also provide virtualization of operating system. However, they differ in a significant way from virtual machines. Virtual machines contain a kernel, and containers do not contain a kernel. This we already discussed in the first slide, right? That virtual machines contain a kernel and containers do not contain a kernel. All that containers contain is the dependencies and the code. Containers require less system resources than virtual machines because they don't run a kernel. So as I said, kernel consume lot of resources. Containers do not contain kernel, because of which they use very less system resources. This allows us to run a few hundred containers versus a few virtual machines on the same set of resources. And then the next point is virtual machines are isolated from other machines, and hence they are secure and resources can be allocated. So one point about virtual machines is that they are isolated from other machines, and hence they are secure and resources can be allocated. I mean, they are not completely isolated at the hardware level, but hypervisors do a pretty good job of isolating two machines from each other. On the other hand, we have containers, right? So how do they achieve security and resource allocations? Containers running on the same machine achieve security and resource allocations using something called Linux namespaces and control groups, which we will discuss later in this video. So continuing, any process running in a container is running on the host machine's kernel. So when you run a process in the container, right, it's not that it does not need a kernel. It definitely needs a kernel, but it relies on the kernel of the host virtual machine. It's not running its own kernel. So multiple containers running on a host will all share the kernel of the host. Containers make use of a technology called LXC. LXC refers to capabilities of Linux kernel, specifically namespace and control groups, which allow sandboxing processes from one another and controlling their resource allocations. Let's move further. So the next question is, do containers contain an operating system? When you install an operating system distribution on your laptop, you get a kernel and a whole series of libraries and utilities, right? Let's say you install Ubuntu on your machine. There are so many things on that particular operating system. Now the question is, let's say you want to run a microservice on the cloud, and you install Ubuntu on a server. All those things besides the dependencies in the OS that are required for running your microservice, do you need all those things that are installed on the Ubuntu machine? You don't need them, right? Let's move further. So most software is not monolithic, it is not self-sufficient. Applications depend on shared libraries provided by operating system. When you run an application, right, there are number of drivers that are provided by operating system which your application uses. Everything is not built into your application. Any programs you install for that OS will be built against the libraries that are shipped with that OS distribution. Let's say you want to run something on Mac, then the code that you will build will be for Mac. And then let's say you want to run something on Windows, so the code that you will build will build against the Windows libraries. And the same goes for Linux. So, but when we build a container, right, all that is required is the binary that you want to run plus anything that the binary depends on. You don't need all the 1000 other things that are installed on the operating system. There is no requirement to package a complete OS distro file system. Binary is not needed by the container. If your binary is not linked against any other library, you can almost get away with a single binary and nothing else. If your application, right, it's not making use of any drivers of the operating system or anything that is provided by the operating system, you can get away just with your single binary and no dependencies in the container. So to answer the question, do containers contain operating system? The answer is that container can contain binaries and libraries provided by the operating system, but it never contains the kernel. It uses the kernel of the underlying host. Moving on. So what's the difference between a containerized process versus a normal process? So as I said in one of my previous slides, that container is nothing but a process running in an isolated sandboxed environment on the host. So what's the difference between a containerized process and a normal process? A container in most cases will run a single process, which is the user application, whatever your program is or whatever your microservice is. The difference between a containerized process and an ordinary process is the restrictions put on the containerized process and changes to how it sees the environment around it. This is powered using Linux namespaces. We can also control the resources allocated to the process. This is powered using Cgroups. So Linux namespaces and Cgroups help in controlling how a process runs on a machine versus a normal process that runs directly on the machine. Let's continue. Let's go through some of the differences that are there between a normal process and a containerized process. So instead of using the host's root file system, a different file system is mounted on slash. So The host slash directory is not mounted into the containers slash directory. It's a separate one. The containerized process runs in a separate process space so that it can only see itself and its children, but not other processes running on the host. So this comes in for the security part, right? Let's say a process sends a kill signal to another process, but when a process runs in the container, right, it cannot send a kill signal to any of the parents process because it cannot see them. And then the next point is a separate user namespace so that the users in the container are different from those in the host. Again, the users are not shared between the containers and the host machine. A separate set of network interfaces with their own IP addresses, and then connect them to the host network interface so that it is able to connect with the outside world. So this is like, let's say you run something on your machine on port 80, right? And there is another process on your same machine which tries to run on port 80. It will not work. But when you run the same process in a container, right, exposing port 80, it will be able to run. Why? For the simple reason that it's running in a separate network namespace. And then now if you want to expose that particular process on your host machine, you can connect your host to your containers network namespace, and that will allow you to access your containers network namespace from your local machine. So as we can see here, there are four different namespaces. One is the file system namespace or the mount namespace, what we mount into the container. The second is the difference in the process namespace. The third is the difference in the user namespace, and the fourth is the difference in the network namespace. So moving on to what powers these namespaces, right? It's something called Linux namespaces, which is the real magic behind containers. Namespaces in Linux can be used to isolate processes, networks, users, and mounts from each other on a single machine so that one is not aware of the other. A parent namespace can see its children namespace and it can affect them, for instance, with signals, but a child namespace cannot do anything to its parent namespace, which is one of the most important ways that containers ensure security. This is necessary for security and protection from malicious code. Moving on. So these are the different Linux namespace which we already kind of looked at. So one is the PID namespaces. This ensures that processes within one namespace are not aware of processes in other namespaces. The second is network namespaces. Isolation of the network interface controller, IP tables, routing tables, and other low-level networking tools from that of the host machine. Next is mount namespaces. File systems are mounted so that the file system scope of a namespace is limited to only the directories mounted. You don't want a container to be able to access all the files on your machine. The next is user namespace. Limits users within a namespace to only that namespace and avoids user ID conflicts across namespaces. Moving on to Cgroups. What are Cgroups? Cgroups allow you to allocate resources such as CPU time, system memory, network bandwidth, or combination of these resources among user-defined groups of tasks running on a system. So we have multiple process namespaces, right? Let's say we have 5 containers running on a machine and we have 5 process namespaces for them. Now we want to limit the amount of CPU and memory and the network bandwidth and the disk IO that each container is given. So that is possible using something called Cgroups. These groups can also be hierarchical, which means that a subgroup inherits the limits administered to its parent group. This means that, let's say there is a container, and though the recommended way is to run only one process per container, let's say for argument's sake that there is a container that is running multiple processes, and so there is one parent process and then there are multiple child processes, right? So these C group limits, right, they also apply to the child processes. Moving on, what's the need for C groups? Why do we need C groups? So the first reason we need C groups is for resource limiting, as we already discussed. Groups can be set to not exceed a configured memory limit, which also includes the file system cache, CPU limit, or network bandwidth. Next point is prioritization. Some groups may get a larger share of CPU utilization or disk IO throughput. So because of C groups, it's possible to allocate different processes different amounts of memory. and different amounts of CPU, different amounts of resources. The next point is accounting. It measures a group's resource usage, which may be used, for example, for billing purposes. We can monitor at a granular level how much resources does a particular container consume. And then the last point is control, like freezing a group of processes, that checkpointing and restart. So we can restart the particular, like in case of virtual machines, we can just hibernate the machine, right? So the same thing Cgroups make possible for containers. So this brings us to the end of our discussion for containers. I hope this video was useful for you and you learned about containers. Do let me know if there are any questions in the comments, and let me know if you would like to hear on other topics.